Hi, everyone. Thanks for joining our webinar. I'm Lori Cooper, and I'm a product manager at the HDF Group. Today, we're going to talk about the Highly Scalable Data Service, HSDS, another acronym, and Keita, which is the commercial product that we've designed around that. Today, your presenter is John Reedy, and he's been a senior architect at the HDF Group. He's been working on this project for about 3 years, and it was originally sponsored by NASA. Some housekeeping issues before we get started. If you'll look at the webinar panel, there's a section called questions. If you could communicate your questions to us in that panel, it's just a little bit easier for us to manage at the end when John starts taking those questions. I will put together the recording of this and any links or anything else, package those up and post those on the forum and send an email next week. We will also continue, we're really trying hard to have about a webinar a month, and I will get some information on what's coming up next and send that out as well. So I will hand it over to John Reedy, and he will start his presentation.
Hello, hi everyone, I'm John Reedy. Welcome to the webinar. So this morning we're going to talk about the Highly Scalable Data Service, and the agenda, one second, is overview of the server, the client libraries, and Keita Lab. We'll follow that with the Keita Lab demo and then a Q&A session. So let's get started. So if you think about HDF, you could think of it as an API, or as a file format, or as a data model. And when we want to go to be effective with HDF in the cloud, we have to drop one of these things. And the thing is the file format. So
hey, John.
When we talk, yes?
I'm sorry, I'm going to jump in. You need to share your screen.
Oh, I thought I was doing that. Am I sharing now?
I do not see it yet. Try this now. I've asked.
Okay.
That's good. Thank you.
Good. All right. Sorry, guys. So when you we want to have HDF work well in the cloud, we'll have to drop this file format idea. So with HDF server, you don't have traditional HDF files in the cloud, but you do have the equivalent of the C API and the data model you're used to. So everything else works just like before. So the idea is to have a web-based service with a REST API. So this enables any number of clients to connect to the service. They can use JavaScript or C or Python, whatever. And rather than storing files in the POSIX file system, we'll be using object storage. On Amazon as AWS, this is called S3. And we want to enable elastic computing. This means that we can enable more CPU power as needed to do whatever computations the server requires. And we want to be compatible to existing Python or C applications you may have already written. Oops. So the challenge with using object storage for HDF5 is that the HDF5 library is not compatible with object storage. So we'll need a different mechanism to get bytes in and off the object storage layer. In object storage, it's very high latency compared to what we're used to with POSIX file systems. Furthermore, it's not read-write consistent. It's eventually consistent, but if you write a few bytes to a storage system and immediately read back that location, you may not get what you just wrote. And for high throughput, it's possible, but there needs to be some trickery to get maximum performance. So we came up with this alternate solution called the HDF Cloud Schema. And what this is we basically shard the contents of what you'd usually find in the HDF5 file into separate objects. So you'll have objects, JSON objects for metadata in the file. You'll have binary objects for the chunks of a data set in a file. So here we represent HDF5 data set, and the heavy lines are the chunks, let's say, of the data set. Each of these chunks gets stored as a separate object in the file. When the client wants to do a selection, say he wants to read this yellow region of the data set, he sends that request to the server. The server is going to pull in whatever objects are needed from the storage system, assemble them to what the client wants, and then return that to the client. So all the complexity of dealing with these multiple objects in the storage system is transparent to the user of the service. And I can, let me quickly change gears here. I can show you how this looks like on S3. So here, this is the AWS Management Console, and I'm looking at an S3 storage bucket. We have a key, hdflab/db/ and now there's this ID, /d and another ID. This is the ID of the data set. And inside this folder, we have a bunch of objects. There's a dataset.json, which describes the metadata of the dataset, the type and the shape, the compression used, and so on. And then you see there's a whole bunch of numbered objects. These are all the chunks of the dataset. So anytime the server needs a chunk, it would do the appropriate S3 call to get that key, pull the data from the storage system, uncompress it, and then serve the pieces of that chunk needed to the client. So let me go back to the presentation. How this works is that the server is implemented as a set of containers. These containers can run either on Docker for a single server or on Kubernetes if you require to have multiple machines to provide more throughput and CPU power for the server. There are two classes of containers. There is the service node and the data node. The service node are the containers that receive requests from the clients. So these containers would get a request, they would authenticate the request, authorize the action that the request wants to do, say, delete an object or add an object. And then they forward one or more requests to one or more data nodes. And on the right, we're showing the object store, and there's this virtual partitioning of the object store. So each of these yellow balls represents one object in the object store, and each data node owns one partition. So when the client needs to read an object that's in this partition, the service node would send the request to the appropriate data node. The data node would read that object. So notice we have this kind of crossbar direction here. Each service node can talk to each data node. Okay, so this allows a few things. One is, if you recall the read-write inconsistency, because the data node owns every particular object, it can be the source of truth for the current state of any object. The other aspect, excuse me, the other aspect is that the data nodes can be a cache. So any objects that have recently been read can stay live in that data node, and we don't need to go back to S3 to fetch that each time. And thirdly, this allows a degree of parallelism. So when there's a request that spans multiple chunks, you can have one or more data nodes working simultaneously to fetch or update the required data. So this allows a degree of scalability. We can have any number of service nodes and data nodes, and the aggregate throughput will scale with the number of nodes you're running. So server features, clients can use the REST API directly. We have SDKs that provide language-specific interfaces. You can read and write any data. We support compression. The performance is scalable. So I was saying more nodes means better performance. And you can deploy it to a cluster, meaning that you're not limited to the horsepower of a given server to do the work that you need to do. So it sounds great. How do we get to this? There's a few options. The easiest, and well, I'll be showing later, is Keita Lab. So Keita Lab is an online environment where we've already set up the server, some sample files, a Jupyter Lab environment that lets you run Python notebooks, and so on. So it doesn't cost anything, and it's very little effort to get started. Second, in order of effort required, is the Keita server. Keita server is our branded commercial offering of HSDS. You can launch it from AWS Marketplace, and what this does, it spins up a new server, your own private HSDS server. And once it's there, you can just start using it. So you have to pay the costs of running the server, and there's a small charge for using the marketplace code that comprises the server. Third option would be to take the open source HSDS from GitHub, build the image of the server, and run that either on your own EC2 instance or on a Kubernetes cluster. And again, you have to pay for whatever AWS costs are incurred. Sorry, that should be option 4. Option 4 would be to take the same code and run it on your own data center. Okay, so even though HS Server was developed initially with AWS in mind, you can run that on-prem with object storage systems such as Ceph or OpenIO. And we provide consulting if you need help in setting up such a system. Oops. So I want to talk about a few new other features that we've developed recently. If you have a large collection of traditional HDF5 files in the cloud, you could shard those files and utilize them in the server, but it may be easier just use those files in place. Okay, and that's what we support now. If you have HDF5 files stored in S3, you can, for read only, connect to those files through the server. And this means you don't have to pay extra costs, say if you want to have files both in the traditional HDF5 format and the sharded format, you just need one format of the files in the cloud. So let me talk about the architecture from the client side. So if you have a C application, you could be using different libraries like NetCDF and so on. It talks to the HDF5 library. So if you now need to access files in the cloud, there's two approaches. One is to use what we call the S3 virtual file driver, and that's included in the most recent version of the library. The S3 virtual file driver works at a low level of the library, and it takes what would normally be a POSIX read call and changes that to an S3 GET request. So this GET request goes off to the cloud, fetches the pieces of the HDF file, and brings it back. And from that point on, it works normally like the HDF5 library. The other option would be the RESTful. The RESTful is a higher level plugin for the library. And this works at a higher level, meaning that there's less transactions back and forth between the client and the cloud. Okay, the other difference is that the RESTful allows reading and writing data. It allows multi-threaded access, whereas the S3 virtual file driver is only read access and only single-threaded. Okay, for Python users, H5Py has been a very popular package for reading and writing HFI files on disk. We have a package called H5PyD that does the same API as H5Py, but it again converts to the REST API and goes off to the server. All right, and finally, you can have web applications that use JavaScript and directly make REST requests and go get data from the server. This allows web applications that don't need any specific web server to run. They're just pulling data from the HS service as users are selecting different values to be displayed. Okay, so H5PyD, again, the Python client is pure Python. It has all the functionality of H5Py and plus some extra features. For instance, you can list contents and folders. You can set access control lists. You have a PyTables-like query interface. And furthermore, other packages like H5 NetCDF X-Ray can use H5PyD transparently. Okay, the RESTfile plugin, again, is for a plugin for C applications that are using the library. They enable this plugin, and the application will work just like before, except now data is going from the server. We also have a set of command line tools. These are tools that let you do things like list contents in the server, create new files, delete files, load files, download files, modify permissions for files. And these are included with the H5PyD package. So finally, there's Keita Lab. So as I mentioned, Keita Lab is an online environment that the HDF group maintains. And it doesn't require you to set up any software or install anything. You just go in the browser, sign in to Keita Lab, and when you sign in, we'll spawn a new container with an associated disk volume. And this container is connected so that you can talk to the HDF server. And the HDF server is set up to read and write to an S3 bucket. So this lets you, from anywhere, go and do HDF applications. And the nice thing here is that all the data movement between the S3 bucket and the HDF server and the HDF server and your user volume is local to that region in the cloud. So all that data movement is not going from the cloud to your desktop, it's happening in the cloud. And the only data that gets transmitted from the cloud to your desktop is what you see in like displays of plots and such. A few words about upcoming features. Recently, we've been working on Azure support, and that should be ready to go fairly soon. We'll be able to deploy it either to an Azure VM or Azure Kubernetes, and we use Azure Blob Storage rather than S3. And all the existing libraries, RESTful, H5PyD, and tools should work as is using Azure rather than AWS. Another feature is Lambda functions. So AWS Lambda is a service that lets you run code without a server, okay, serverless functions. And the advantage of incorporating these into HSDS is that you can have the scaling. So we talked about scaling from the service node to multiple data nodes, but with Lambda, you can scale from the service node to 1,000 Lambda functions. This will allow very high access to doing things like time series selections over a really large data set. Another future project is direct access. So the server is nice, but sometimes it's convenient to be able to directly work with the storage system. So this is more like the traditional HF5 library, except that we are reading and modifying data in this sharded format for HDF. This will allow things that are you can't really do in the library currently, such as multi-threaded access, multiple writers, multiple readers to the storage system. It's very handy when, say, you want to spawn thousands of workers that are simultaneously reading and writing to a given HF5 file. That would present challenges to scale up the server to handle that load. But with direct access, it doesn't matter because each client is directly talking to the storage system. We've worked with NREL for a couple of years now. They've set up a 50 terabyte set of data on S3 that presents about 30 different data sets. Each data set is more than a terabyte in size. And the advantage of offering this data to their users is that, one, users don't need to download 50 terabytes of data. Two is it's very efficient to access this data for any given time or any given latitude and longitude. So you can slice and dice the data in different orthogonalities. It's been very popular with the NREL's users, and the server has been running for more than a year now, and it serves thousands of requests a day. All right, here are a few references, and that's the end of the show. So let me switch gears and show how Keita Lab works. So if you go to the HF Group website, you can create an account if you don't have one. And if you do have one, you can log in to your account. Once I do, there's this Keita Lab link. And there's some information about how to sign up for Keita Lab. Lori has created a video that walks through step-by-step what you need to do to sign up, which is not very hard to follow. Okay, so there's a license agreement, and I've already gone through this, so I will just go to the HF Keita Lab link, and then you sign in with your HF Group site credentials. Okay, so let me kill this. So this is the Jupyter Lab interface. So Python notebooks are a handy way to do kind of interactive data explorations. And with Jupyter Lab, you have basically what are Python notebooks in the cloud. So if we come here, we have a HF Lab FAQ, which describes different aspects about Keita Lab. There is a terminal you can run. And I described that there are these different command line tools for HF server. One of these is hsinfo. So if I run that, I see it says our server is Keita for Keita Lab, server state is ready. Here's endpoint, I have a username and password. I have a home folder. The home folder is a folder maintained by Keita Lab where you have permission to create new files. So every user who signs up gets their own home folder, and you're allowed to have up to 100 gigabytes of content in that folder. The node count is 8, so that means that there are 8 server nodes, 8 data nodes currently. This number can change based upon how we scale up or scale down the server. It's been up for 12 days, and my H5 PyD version is 0.5.0. Okay, so in this command line version, I have a disk system, right, you'll have 10 gigabytes of normal POSIX files. So if I have a HDFI file on my desktop, I can upload it into this POSIX folder. So I go here and I say upload. I can choose an HDFI file. Okay, now this file is in this small POSIX file system in Keita Lab. So if I do h5ls-r tall.h5, I can see the content. Okay, so this is a normal HDFI file. Now let's upload this file to my home folder. So there's a command, hsload. I take the file name and I give it the path to upload to on the server. So I'll load it to my home folder. Okay, so it takes a second while it makes sure everything is synced up to S3. And now if I do, instead of h5ls, if I do hsls-r home jread tall.h5, I see the same content. Okay, so it looks almost exactly the same as what I get for traditional HDFI files, except here it's a sharded representation of that content that is stored, in this case, on AWS S3. Okay, now this file, this data, is in this bucket that's shared with all other Keita Lab users. But you may not want your content to be visible to others, and in fact, by default, the content is only visible to you. There's a command that lets you update the permissions. So if I do hsackle, and again with the file name, okay, I see ACL stands for Access Control List. And in this case, there's one ACL, which is my username, and I have permissions to do everything, as you can imagine. If I would like other users to be able to read this content, but not modify the content, I can say hsackle plus R for read default, meaning any users can do this action. If I had a specific user in mind, I could say this plus R and then their username, and only that user's ACL would be added. So we did plus R default. And now if any of you happen to be on Keita Lab, if you do hsls/home/jread/tall.h5, you'll be able to see this content that I just uploaded. And finally, we can take content back from the server to a regular file by saying hsget home jread tall.h5, and I'll give a different name, foo.h5. And now we have our regular file back again. So we've kind of did a round trip, right? We've taken a regular HDFI file, uploaded it to the cloud in a sharded format, and then download it back into a regular HDFI file again. All right. So next, let's look at some of the samples. So we provide both sample data and sample notebooks. If you go, when you first log on, you'll see there's a folder called examples. We have a tutorial, and it steps through ways of doing different things in HDFI. The command line tools, working with data sets, working with compression, working with groups, working with attributes, advanced types, doing plotting, and queries. So like for plotting, so again, we import h5pyd. Here's a file name. It has an ID. Let me clear this. has a shape. In this case, it's 8,000 by 8,000. You have the chunks. So all these operations work pretty much like they would work with regular HDF files on disk. And here I can do a grab. Here I'm going to take a step view. So the image is rather large. So I'm going to pick every 8th row and column and read that as an array in memory. And now I can do a plot. So here we see a plot. So I was able to get this data that's in S3. And the nice thing about Jupyter Notebooks is that you can combine code and print output and plots to visually see your data. All right. Next, again, all these examples are there for you to do and understand more about how the system works. I want to show an example that illustrates kind of the performance differences between these different ways of access. So if I go to next benchmark, clear all outputs. So this is a data set that is about 12 terabytes in total. So it's satellite data from not satellite, sorry, it was simulation data from climate models that is stored in S3. The initial data was provided by NASA. Amazon is hosting this data, and through Keita Lab, we're able to access those files. And again, these are traditional HF5 files, but we are able to read those files through the HF server interface. Okay. In this example, we're going to illustrate 3 different ways of accessing this data. Okay, and they are local, S3FS, and REST. So local would be I take one of these files from NASA's S3 bucket, I copy it into my local POSIX drive, and then I do normal HDF5 operations on it. S3FS is a way of accessing that file directly in the cloud, where I don't need to download that to a regular file first. And REST would be using the HF server to access the data. And it'll be interesting to see how the performance varies with these different modes of access. So first, let's do local. So here I have an if. I say if it's local, I'll import H5Py. And we're not doing that. And here, since we're local, I need to download the file to my local file system. And that's what happens with this wget and the S3 URL. So now I'm downloading. This file is about 1 gigabyte. And normally that'll take a long time to download. But since we are already in the cloud, right? This notebook is running in the cloud. You get pretty fast download speeds. And in about 20 seconds, we've downloaded this file to my local file system. So if I go back to my terminal, I see that now there's this 1.1 gigabyte file that was just created. Okay, so now I'm going to open the file with H5Py, and this % time says, show me how long this took. So pretty fast, 800 microseconds. And I can read an attribute. That was also fairly fast. I can get a data set. I can look at the chunks. So here the chunk layout is 1 by 369 by 836. And the data set size is almost 4 gigabytes. So that's a lot of data to read at once. So let's read one slice out of that data set. and see how long it takes. So we're going to read an 83 megabyte slice of this three-dimensional data set. And that took 300 milliseconds. We can see the data, and we can do a plot. Okay, and then finally, let's do a time series. So here I'm accessing data in the opposite orthogonality. I'm drilling down through this data cube to get a one-dimensional data set, and I can plot that. Okay, so let's remember these times and switch our mode to S3FS. So in this mode, we are still using H5Py. The difference is that rather than downloading the file first, we just access the file in place. This is really handy if you don't need to access all the data in the file, or it's a really large file where you may not have space to store that locally. So again, open was fast, 281 milliseconds. All these operations report the same results as before. You have the same chunk size. Okay, so now let's read a slice from this file. So recall, it took 353 milliseconds accessing the file locally. Now we'll access it in the cloud. Okay, it took 2.77 seconds. So a bit slower than accessing it locally, but the advantage is we didn't have that 20 seconds of downloading to get the file locally before we could read it. Okay, we got the same results, same plot. Now, again, let's do the time series extraction. So here we're going against the grain, so to speak, in accessing the chunks. So more chunks will need to be read. That means there'll be more back and forth between our notebook and the storage system. So we had 222 milliseconds with local files. And it'll take a while. So 10 seconds. So here, the difference between local and access for in-place files in the cloud was quite a bit more, right? 10 seconds versus 300 milliseconds. Okay, finally, let's try this with the HDF server and see how that compares. So I'll set this to rest. This time we're importing the H5PD library. I'll just do a check. We still have our 8 nodes in this case, and we will get there's no downloading, so that's fast. We open the file with H5PD. That only took 32 milliseconds. I can list the content. I can get an attribute. Here, getting an attribute took just a few microseconds because when we did the initial file open, we cached most of the attributes for different data sets and groups and such, so they don't have to go do a round trip to the server each time. Get the data set. This is a little bit interesting. So when you do chunks, in this case, rather than getting a tuple, we get layout information. So in this case, we are referencing the original source HF5 files, and there's a key here called file URI. This is the location in S3 of the original HF5 file. And then there's a chunk table that stores information in HF server for the location of every chunk in this file. Okay, but anyway, reading the content works just like before. So let's read the same slice. So it took 2.77 seconds with S3FS, and reading it with the HF server took 1 second. so better performance. And that's mainly because two things. One is that there's less chatter going back and forth between the notebook and the server compared to the notebook going through the HDF library. And the other thing is that the server oftentimes can parallelize these requests to get the results faster than you could with a serial access. So if we run this again, it's slightly faster. So as we change the slice, we will get advantages of caching or not. So here, this slice wasn't cached. It took 6 seconds. When we access it again, it goes down to less than a second. So, but the server, by keeping track of recently accessed data, it avoids having to go all the way to S3 to fetch the data. Okay, same results. Okay, now let's do the time series. So recall the time series took 10 seconds with the S3FS driver. Here we're going through the server, and we got the result in 100 milliseconds, right? So 100 times faster than with S3FS, and actually faster than we got with the local HFI file, right? And the reason that we do so well in performance here is that here's a case where we're accessing many chunks in the data set. Those chunk accesses can be parallelized through the multiple containers on the server, and we're getting this effect of harnessing more computing power than we'd have just with our single notebook session. So again, there is caching going on. Let's rejigger this to use a non-cached value. This should be a little bit slower. So 500 milliseconds. And again, if we run this, it's much faster, right? Because all those chunks got cached into the data node chunk cache. All right. But unfortunately, this is not a very exciting time series. All right. Okay, there's a lot more to explore in Keita Lab, but this will be all we have time for today. So again, I would request you give it a try, sign up Keita Lab and try yourself running through the different examples and data sets we have. Okay, with that, let's open it to questions.
Yeah, so just as a reminder, we have that questions panel as part of the GoToWebinar panel you guys should see. If you can submit your questions there, it's just easier for us to kind of handle and organize. And, you know, if you think of anything later, email help@hdfgroup.org and we'll get those answered and posted on the forum as well. So I think we have one question there, John.
Yeah, this question from Jacob, what kind of performance do you see on writing? Yeah, pretty much equivalent to what you see with reading. Again, if you're doing writing, say, in chunk size blocks, I think performance would be a little bit worse than you'd have with local files. If you're doing writing in terms of, say, strided access across many chunks, you'll get the same kind of acceleration of being able to harness the power of the multiple containers to do your writing. Okay. Oh, and one other thing I want to say is that what we did, say when we were creating this NREL example, the 50 terabyte file, if I had to create that content through one process, it would take some time. But since with the HDF server, you can have multiple writers working simultaneously. What we did is we we spawned up multiple machines with multiple processes and had all those processes writing sections of the file simultaneously, right? So this greatly speeded up the operation, right? So that's a capability you have with HDF server that you don't have with HDF5 library unless you're using the parallel HDF5 and MPI and such. All right, do you have any other questions? Oh, here's one. I'd love to hear your thoughts on the ZAR library and how it compares to HSDS, particularly with H5PyD direct blob access you were talking about. Yes, so let's go back here. So it's interesting that the HDF schema was developed fairly contemporaneously with the ZAR format, and they're very similar, in fact. So ZAR has a similar scheme where there's JSON objects that store metadata, and chunks are stored as objects. And they even use the same kind of indexing scheme, except in ZAR, I think it's 0, 0, 0, where we have 0 underscore 0 underscore 0, but the same kind of structure. One difference is that in ZAR, they actually map the HDF5 hierarchy directly into the S3 storage schema, meaning that if I have a data set that's like a /G1/G1.1/dataset 1.1.1, that gets stored in the key /G1/G1.1/dataset 1.1.1. You'll notice with the HSDS schema, we don't do that. It's basically a more flat hierarchy. You have this folder, which stores all the content for that file. And it's stored by the file ID, not by the file name. This lets us do things like rename the file without moving the contents around. And then rather than having objects by their HDF5 path, we have a subfolder D. There's another subfolder called G that you don't see here because we don't have any subgroups. But the D folder has all the data sets in the file, again, stored by ID. So the advantage of this approach is that in cases where you have multi-link setups, okay, so in HDF5, you don't need to have a strict tree of objects. You could have, say, a folder, a group G1 and a group G2, and have both G1 and G2 linked to the same data set. So you have cycles in your tree. If you're directly mapping those H5 paths to S3 paths, you couldn't do that. The other advantage is, again, that we can rename links or create new links without moving the contents of the data sets when we do that. Okay. Other than that, I think as we move on to this direct access project, I think the performance we'll get compared to ZAR will be fairly equivalent. So the schema is similar, and the difference, I think, though, with ZAR is that ZAR is not a service, right? ZAR is just a way of storing content. You won't have the capability of using a service access. So direct access is good, especially when your workers are in the cloud close to the storage system. If you, say, are accessing data remotely, then the cost of getting all the data directly from S3 downloaded through the internet will be prohibitive. So with HSDS having a server and then having this direct access capability, you get to choose, whatever is optimal for your particular application. The other thing is that because we have the vol, you can access HSDS sharded data through C or Fortran applications. And I think currently, I don't think there's only a Python package for ZAR access. All right. Okay, so I hope I covered that well enough. Let's see. Does HSDS integrate with the DAS distributed compute framework? Yes, it does. So I think HSDS works well with Dask because, especially for Dask running, say, in a Kubernetes cluster. So in the cluster, you'd have your Dask workers that need to read HDF5 data, right? Having the workers access content through a server means that we can have parallel requests come in from the Dask workers to the server. And the only trick then would be you want to scale up the server to meet the load of the number of Dask workers you have, right? So with HSDS and Kubernetes, there's a single command to scale up or scale down number of pods. So that should be fairly easy to do. The trick will be kind of calibrating, what the respective workload you want for the server and for the Dask workers. All right. Okay, any other questions?
That looks like we might be through with questions. Again, if you guys think of anything, you can email it to help@hdfgroup.org and that will get routed to us. We'll compile the questions asked and post those as well. So maybe with a little, if we need to flesh that out versus being on the cuff, we'll take care of that as well. So again, thank you everyone for attending, and we will get the information posted and let you know about other upcoming webinars. And thank you very much, John, for presenting today.
Yeah, thank you. And thanks everyone for attending. Bye-bye.